LLC Resonant Converter based power supplies use 3-element resonant circuit with a capacitor and 2 inductors, which achieve good efficiency for high power systems at wide output load regulation ranges using high operating frequency, which reduces size, component count, and eventually the cost of the system. These type of converters were quite tricky to understand, but not anymore. Just like every resonant converter, an LLC resonant converter is made up of 3 blocks: the power switches, resonant tank, and rectifier circuit. First, the MOSFET switches and converts DC voltage into a high frequency square wave. The square wave then enters the resonant tank, which eliminates the square wave's harmonics and give the output as a sine wave fundamental frequency. The sine wave is transferred to the secondary side of the converter through a high frequency transformer, which scales the voltage up or down according to the output requirement. And lastly, the diode rectifier converts the sine wave into stable DC output. This is how an isolated resonant converter works. The power switches of this converter can be implemented in full bridge or half bridge topologies, and each has a unique output waveform. The main difference between these topologies is that full bridge topologies generate a square wave output with no DC offset, having an amplitude equal to the input voltage, which ranges from plus Vin to minus Vin. The half bridge topologies give a square wave that has offset by half of the input voltage. So there is a difference of amplitude in both of these topologies. Each topology has its own advantages and disadvantages. A full bridge topology requires more transistors, which makes it more expensive. Also, due to number of transistors, there will be more RDS on in the circuit, which can increase the conduction loss. On the other hand, a full bridge topology reduces the transformer turns ratio by half, which minimizes the copper loss in the transformer. A half bridge topology is more cost effective to implement and has added benefits of RMS current across the capacitor, which reduces up to 15%. But it also increases the switching loss. Considering these trade-offs, it is recommended to use a half bridge power topology for applications where power is below 1 kW, and a full bridge topology for application with a higher power. You must be thinking, why only we use LLC resonant circuit in the isolated resonant converter? Why not just LC or any other resonant tank? Well, there are mainly 2 reasons for that. Whenever we design a system, it should be cost competitive. In general, half bridge topology provides lowest cost switching network. On the other hand, we can find a resonant tank that can use the parameter of the transformer. If we can do that, we can cut down the additional component count for the resonant circuit. An ideal transformer has its magnetizing inductor in parallel with its input winding, and we can use this as the resonant inductor in parallel with the resonant tank output port. And in the real world, a transformer always comes with a leakage inductor in series with the transformer winding. If we somehow use this series leakage inductor as a resonant inductor, we can reduce the cost of the circuit. Among the many 2-element and 3-element resonant tank circuits, which we have seen in the previous video, only one circuit can utilize both the transformer leakage inductor and magnetizing inductor as the resonant inductors. And that resonant tank would be a 3-element LLC resonant circuit. And with the half bridge switching network, we get the lowest circuit cost. There is another advantage of the LLC resonant circuit. This resonant tank is made up of resonant capacitor and 2 inductors. The resonant inductor in series with the capacitor and transformer, and the magnetizing inductor in parallel. The tank's role is to filter out the square wave's harmonics and provide the sine wave of the fundamental switching frequency at the input of the transformer. As we have seen in the previous video, the resonant tank has a gain that varies according to the frequency and the load applied to the output side. We can say a power supply is robustly designed when it can handle a good amount of load regulation. And if a resonant circuit's response changes with load, that creates challenges for design. We must tune the resonant tank's response considering the switching frequency and output load to ensure that the converter efficiently operates across a wide range of loads by designing the tank's gain to exceed unity for all load values. The LLC converter has a wide operation range due to the resonant tank's dual inductors. To understand how this works, we'll consider the tank's response to heavy and light loads as per the requirement. Let's consider the whole secondary side of the transformer as a load to our resonant tank. Let's see a resonance gain for a range of loads if the resonant tank was consist of the resonant capacitor and the magnetizing inductor only. At light loads, there is a clear peak in the resonant tank's gain. However, the gain of the heavy load does not go to peak. Instead, it has a damped response and only achieves unity gain at higher frequencies. Now, if the resonant tank is only made up of resonant inductor in series with the resonant capacitor, the behavior is different. The gain does not exceed unity, but when the load is heaviest, the tank reaches unity gain much more quickly than it would with the parallel inductor. So by implementing both of these inductors in the resonant tank, we get a resulting frequency gain response which ensures that the converter can respond to a much larger range of loads. Also, it can enable stable control of the entire load range. So the LLC tank has two resonant frequencies, and these are the formulae. The series resonant elements LR and CR resonate with the parallel resonant element LM to provide the parallel resonance of the LLC Resonant Converter with the resonant frequency FM. And the series resonant elements resonate by themselves to provide the series resonance of the LLC Series Resonant Converter with the resonant frequency FR. Therefore, this can either provide a voltage step-up function utilizing the parallel resonance or voltage step-down function utilizing the series resonant characteristics. Let's say the effect of resonant parameter variations. When we see the response, with the increase of the ratio Lm by Lr, the peak value of the gain curve decreases. That means the voltage regulation range is reduced. If the Lr by Cr ratio is increased, the difference between two resonant frequencies increases, which means the operational frequency variation increases. So both the ratios need to be low enough to have a wide voltage regulation range and narrow operational frequency variation. However, the current ILM is circulating between the switching network and resonant tank at the input side, and it doesn't transfer to the output side because of the isolation. If the LM is reduced to keep the Lm by Lr ratio low for a wide voltage regulation range, ILM will increase and therefore it will reduce the efficiency of the converter. Hence, a trade-off between efficiency and voltage regulation range must be considered during the design. So as we have seen, the converter's efficiency comes from the resonant circuit. The resonant circuit of the LLC converters enables soft switching on both primary and secondary sides. It enables zero voltage switching on the input switches. In addition, if the switching frequency is between the two resonant frequencies, we can achieve zero current switching on the output rectifiers. An LLC topology saves board space. LLC topologies do not have an output inductor, which means that all of the inductors can be more easily integrated into a single magnetic structure to save area and cost. So in a nutshell, it is possible to push the switching frequency higher to reduce the converter size while still maintaining higher converter efficiency by using LLC Series Resonant Converter. For example, we can design a 1 kilowatt output LLC series resonant converter with a whooping switching frequency of 1 MHz with gallium nitride FETs and achieve its efficiency up to 95%, and still its size and weight would be so less that it can fit in our tiffin box. That's why the LLC resonant converters are used in power supply application with delicate systems such as high-end consumer electronics, servers, and telecom stations. I hope you understood the importance of LLC resonant converters. Next time, we'll see how this type of converter work and achieve zero voltage switching. I have added all the references related to these circuits in the description. If you have any query, you can ask me in the comment section or email me. Hit the like button and subscribe to my channel. And finally, thank you so much for watching this video.